Okay, we are going to talk about electrical potentials in neurons. So basically, we're going to talk about three types of them that are essential for transmitting information: the resting membrane potential, local potential, and an action potential. Okay, so the resting membrane potential, it's the value of the electrical potential across the membrane when a neuron is not transmitting information. That is that minus 70 millivolts. It's a steady state condition with no net flow of ions across the membrane. The cell at its resting membrane potential has no net charge in the total distribution of ion across the two sides, although individual ions are still going through those little leak channels all the time. Okay, so when the cell is resting, the cell membrane serves as a capacitor. And what a capacitor is it's something that stores electrical charge. So, by separating the electrical charges on either side of the plasma membrane, it allows the neuron to store electrical charge for when it needs it later to transmit information. So the unequal distribution of the ions across the membrane, that is the important part, because the unequal distribution is what allows the neurons to be electrically excitable in response to a stimulus. Okay, so the cell membrane and having those gates that open and close that we talked about in the last section, that's what allows the cell membrane to act as a capacitor and store charge. Okay, so there are two different forces at work that determine the ion distribution across the plasma membrane. There's a concentration gradient and an electrical gradient. So the concentration gradient means that there is more sodium outside the cell than there is inside the cell, and there's more potassium inside the cell than there is outside the cell. The electrical gradient is the difference in charge. It's that minus 70 millivolts. It's that much more negative inside the cell than it is outside the cell. So those opposing chemical and electrical forces control the movement of the ions. Equilibrium occurs when there's no net movement of an ion across the membrane. So if you were to open all the gates, it would eventually all equalize. You would have no electrical gradient and no concentration gradient, and the neuron would cease to be excitable. So having those gated channels that can be opened or closed very quickly, that allows you to store the charge, and it allows you to release it when necessary. Okay, so we talked about this in the last section, the electrical chemical gradient in neurons and the resting potential of the membrane are maintained by those big fat anions, negatively charged molecules trapped inside the neuron. They're too big to go out through the holes, basically. You get passive diffusion of ions through the leak channels. That helps maintain the gradient. And then that sodium-potassium pump that takes ATP to run. And it takes 2 sodium out and 1 potassium in for every molecule of ATP that it uses. So as long as the cell has ATP, then you can maintain that unequal distribution of sodium and potassium. So that's important because, I mean, that's the reason that we ate lunch today or dinner, something like that. So we can do cellular respiration, metabolize that energy, make ATP, and use it to keep that unequal distribution of potassium and sodium. So we have that resting membrane potential. And so potential is always, it means there's energy stored somewhere and we can do something with it later on. So we're using ATP to build up those energy stores, basically, just like we do in our other cells. But the neurons are specialized for transmission of information and processing of information. So when you selectively open ion channels to allow the passage of specific ions, it alters your membrane potential. Okay? So, with nerves, you get sudden, brief changes. And we talk about two changes in resting membrane potential. One of them is depolarization, and the other one is hyperpolarization. You can also sort of think of repolarization, but the two changes that we're going to talk about are depolarization and hyperpolarization. So when a membrane is depolarized, when the potential becomes less negative than the resting potential. So it increases the likelihood that the neuron's going to generate a transmittable electrical signal. It's an excitatory state. When the membrane becomes less negative, it is depolarized. The neuron's getting excited. When a membrane is hyperpolarized, when the potential becomes more negative than the resting potential, and that decreases the neuron's ability to generate an electrical signal, so it's inhibitory. Okay? So I really want you to know those things. So if I said what happens when the cell membrane of the neuron is depolarized, I would want you to respond that the potential becomes less negative than the resting potential. So maybe you'll go from a 70 millivolts up to a 50 millivolt. So the neuron at that point might generate a transmittable electrical signal. It's becoming excited, it's going to fire off. Okay? So there's another, besides those sudden brief changes in membrane potential, you can also get gradual, longer lasting changes in membrane potential, and you call that modulation. There can be, in modulations, basically small changes in the electrical potential that alter the flow of ions across the cell membrane. So there are, like we have our neurotransmitter molecules, there are other molecules that are considered neuromodulators that bind to proteins in the cell membrane, and they alter the flow of ions. They are longer lasting, and they are more gradual. So the effect of a neurotransmitter is fast, and it's over quickly. The effect of a neuromodulator, it's slow, and it lasts longer. Okay, so we're going to look at some of these. This is just a little restatement of that. Changes from the resting membrane potential. Depolarization is when the membrane potential becomes less negative than the resting potential, and that is an excitatory state. Hyperpolarization is when the membrane potential becomes more negative than the resting potential, and that is an inhibitory state. So there's an 11-minute video about resting membrane potential that's pretty good. It's a good explanation of it. There's another video that really goes into detail about how the sodium-potassium pump works to maintain the potential. There's tons of calculations about the chemical gradients and all of those stuff, and gosh, we don't need to know that. Chemistry geeks like myself might be really into it, but we do not need to know that for our course, and so you can watch it if you want, and it's a really good explanation of the pump, but you can just blur your eyes during the part about the calculations and don't listen to that. You will not need to know that for any exam in this class or any other exam in the PTA program or for the PTA board exam. So it's great information, but we don't need to know it. Okay, we already talked about membrane channels. There's some little videos on membrane channels which are pretty cool. We will, in the next section, talk about local potentials and action potentials. So we talked about the three different things: resting potential, local potential, and action potential. So in the next section, we will start going into local potential and action potential.